All right, so welcome to Math 409 problem solving. What I want to do today is talk very briefly about the Great American Shootout, then talk a little bit about games, and then go to an integral that I wanted you guys to think about. So if you are not happy with your midterm score, either after the first exam or after the first two, you can also present additional things to the class. We'll do some more Project Euler problems later. There is a really nice problem called the Great American Shootout, and it goes as follows. So, Great American Shootout. And there's a really readable paper about this. So you have N people, longest basket wins, okay? And then you shoot one at a time. Only shoot once. So would you like to be the first shooter, second shooter? And the answer, you want to be the last shooter. And this is something where I don't want this taken out of context. You know, Professor Miller says I should be the nth shooter. The nth shooter in the basketball game. Okay. Why would you want to be the nth shooter?
You know exactly how far you take it from.
Right. So what would happen if everybody in front of you misses? Yeah, you basically, so we will assume that everybody is competent enough to make a basket from essentially zero distance. So there is a tremendous advantage in going last. The question is how much? As a function of n, what's the probability of the first play winning, second, and so on and so on? I think the paper is like a true mathematician and starts counting with the 0th player. Sometimes it makes the formulas a little bit nicer. And so the question is, how do you analyze this? Well, I don't want to go through all the details. I want you to think about this. If you do want to present this to the class, I'll send the paper to you. When you have a complicated scenario, a great way to attack problems like this is often to look at a simple game state and work backwards from that. So you all told me already one game state where you know what to do. So what does the last shooter do? So analyze by working backwards. So where does the last one shoot from?
The longest made shot.
Yeah, last shoots from longest made. And there's a small issue with this. It's whoever has the longest basket wins. So technically you would shoot epsilon further back than the previous maximum. So what the people who wrote the paper said is, you know, screw this. Let's just say if there's a tie, whoever shoots second, we're going to continue to favor them. Not only do you get to see where everybody else shot, but you win on the tie. So we're not going to have to worry about this epsilon difference. Otherwise, you would just put in an epsilon and take the limit as epsilon goes to 0. It's absurd. Okay, so now we know where the last shooter goes. Where does the second to last shooter go? Can you give me any bounds on where they go?
Longest made.
So if it's the minimum from the longest made.
Like the minimum distance they would shoot from is the
Oh, okay, good, yes.
longest.
Second last shooter is at least as far as the longest made. And I think actually you could figure out very easily where it would be. If the longest made, the way they do the paper is they say your distance from the basket is your probability of either hitting a shot or missing a shot. Is what's the right scale to look at for this problem? The scale to look at is the probability of making it. We are going to assume that all players are equally skilled. Everybody has the same probability. All that matters is how far back are you. And so imagine that the furthest made is from a shot that only happens 30% of the time. Would you want to shoot further than that? No. You know, you already have only a 30% chance of making the shot. If you go back even further, you're going to have even less of a chance. So if the probability is 30%, in fact, anything less than 50%, you would just shoot from there. What if the probability of making the shot is 80%? Would you want to shoot from there? Because remember, the next person after you has the same probability distribution as you. So if you can make the shot 80% of the time, they'll make the shot 80% of the time. Where would you want to shoot in that case? Where? How much further?
Because I want to take into consideration how many people are behind you.
Well, we're talking about the second to last person. So if the furthest shot that's been made is a shot that can be made 80% of the time, we know you have to shoot at least from there or you're an idiot, right? Because if you shoot from any closer, you've automatically lost. So you clearly have to shoot from at least 80%. Would you go back further? Well, if you make that shot, the next person has an 80% chance of beating you. So how far back should you go? Yeah, I would go all the way back to 50%. So if the longest shot is an 80%, I would backtrack to 50% and shoot from there. And so we can figure it out. So if less than 50% shoot there, if greater than 50% shoot at 50%. And so the idea here is we can try to keep working backwards. We know what the last person does. Now we figure out what the second to last person does, and we keep going on and on and on until we can get all the way to the first person. So there's a lot of problems that can be handled like this. What I want to do is I want to do one of the variants of the pirate problems. Does anybody know any pirate problems? When I was at Brown, there was a rule that in any talk to the graduate students, you had to involve pirates at some point. And I think I have the record for the most clever, unexpected use of pirates in the history of the seminar. So the pirate problem I'm going to have is the following. You have 5 pirates. This one, oops. I'll give this one an eye patch. I'll give this one some kind of bluebird, okay? And I will give them the wonderful names of 1, 2, 3, 4, and 5. And you have some loot that you're trying to divide up. So maybe you have N coins. And the way it works is the following. A pirate proposes a division. You know, go 1, then 2, then 3, ... Propose division if 50% or more agree, do so. Else, kill proposer, next proposes. Does everybody understand the rules? So pirate 1 is going to suggest a division of the booty. Pirates 1, 2, 3, 4, and 5 will then decide whether or not they think this is a good idea. What do you say if it's 50%? You can't say majority. So if at least half agree, then that division is done. You could modify the problem to you need a majority, and then that would change the answer a little bit. So if at least half agree, then it's done. If it is not agreed to, you kill the person who proposed, and then the next pirate proposes. And you keep going until you get to a division where a majority of people agree. Do you think we will eventually get to a division where a majority agree?
Possibly. I feel like 5 would vote no for all of them.
Well, but I'm saying, will we, no matter what proposals are made, will eventually some proposal be accepted?
Yeah,
Yeah, why?
because 5.
The last is the only person that
Right. You know, you can have at most 4 field proposals, then 5 is left, and I think 5 will vote for their proposal. So the game will definitely end. So how do you think we should try to analyze this? What might be a good way to try to analyze this? Yes. Subliminal message, right? Work backwards, right? There was a reason we started off with the Great American Shootout. I've been saying for a couple of days I wanted to be talking about this in class, but I wanted to have enough time to go into the pirate problem. Let's work backwards. So if we work backwards, what happens if we get to 5? So it's going to be 1, 2, 3, 4, 5, and it will be 0, 0, 0, 0, n. So now pirates 1, 2, 3, and 4 know that if we reach pirate 5 gets everything. Okay. What happens if we reach 4? Yes.
Strategy because
Well, what will happen if we get to 4? What will it be?
0, 0, 0, and then question 4 and 5. But I feel like
It would be 0 and n.
I feel like it'd be n and 0.
Well, what is pirate 4 going to propose? Remember, you need 50% or more to approve. Yes, you get to vote. Yeah, pirate 4 is going to propose, I get everything. Right? This is why it's extremely important as to, is 50% enough to pass, or do you need a majority? If you need a majority, 5 is going to be like, no, I think I'm going to vote against your proposal and take everything. But if you only need 50%, then this is enough. All right, so now we know if we get to 4. What if we get to 3? What will we have? What would 3 propose? We know at least what 3 is going to propose to the dead pirates 1 and 2, right? How much is 3 going to offer to 1 and 2? 0, right? They're dead. So now, how is pirate 3 going to divide up the loot?
Okay, so the problem is like a little bit to pirate 5
Yes,
and
Yeah.
everything to yourself.
n minus 1, 0, and 1. That's enough to get pirate 5's vote. Because pirate 5 knows if I don't vote for you, you die and pirate 4 takes everything. Is this fair that pirate 3 is getting n minus 1 and pirate 5 is only getting 1?
Not really.
Not really.
But 1's greater than 0. So.
Now, there are many different levels you can analyze this game. If you were pirate 5, would you take this deal?
Depends on how much 1 is worth. If 1 is worth more than like the disrespect that I would feel from
This,
I could just say no just to spite that person.
are there any Seinfeld fans here? There's an episode of Seinfeld where he returns a shirt to a store and they ask him, why are you returning it? He goes, out of spite. They go, that's not a valid reason. Okay, then I'm returning it because it didn't fit well. No, I'm sorry. You said you're returning it out of spite. Once you've said that, you can't change your mind. We will not accept the return. So if you're playing this game multiple times, well, of course, it's hard to do when you kill people off. But a lot of times your strategy is different if you know you're going to be playing it multiple times. If you're going to have to be living and plundering with these people again, the disrespect you feel from pirate 3. Now, it's also different, I think, if you can talk to people. Imagine you can talk to people. What could pirate 5 say to pirate 3?
Either give me more coins or I'm going to vote against you.
Yes. And yes, I understand that I will not be as well off if I vote against your proposal, but you'll be dead. And I think your life is worth something to you. Right?
Yeah.
So after talking to 5, what might the proposal be?
Or more.
Yeah.
Wow.
How much more?
N minus 1.
Yeah,
What did you say? Everything. It could go all the way down to 0 and n. Where pirate 5 can say, look, if you don't give me everything, you die.
But then they would just entice 4.
So now in a situation like this, if 5 is now being difficult, now what can pirate 3 do? Go to 4. So now, what if now maybe you go to talk to 4? What might you now propose?
0 and minus 1 and 1 and 0.
And so actually, let me make these green. So what I love about these problems is it's not clear necessarily what the answer is going to be, and we have to add some additional constraints. If 5 starts becoming too problematic and say, look, I want a lot more, I'm going to let you die, 5 can then just go to 4 and say, look, you want to support me? I'll give you some stuff. I can go to either 4 or 5. Either one of you, I just need one of your votes. And now as soon as 5 starts talking about that to 4, what could 4 say to 3? I'm sorry, as soon as 3 starts talking to 4, what could 4 say to 3?
Yeah, the same thing.
The same thing. And so maybe it goes down to 0 and n. So when you start to think about this, it's not necessarily clear what the answer is and how it would actually be if you play it. So if you were playing this, if you were 3, what would you offer?
Offer 4 and 5 each and over 2. And you get to live.
And so you take nothing.
I would offer them however much it would take them to vote for me.
So one thing is are you doing this publicly? Where people are discussing and then committing, or are you voting in secret? It's not clear necessarily what the right strategy is and what will happen. Who do you think is more incentivized to support you? I think 5 is more incentivized than 4. Is that, hey, 5, I'll give you something reasonable. And you know what, if you don't take it, what do you think 5 would consider reasonable? So I mean, n over 2 sounds fair. I'll give you n over 2, I take n over 2, we split it equally, we screw 4. Why might 5 not take that? Well, 5 can say, look, if you don't give me more, I'm going to have you killed. And 5 says, that's fine, but if I'm killed, you now get nothing because 4 is going to get everything. I think splitting it 50-50 is fair. So again, it would be fascinating to play this game, with say, 100 people on campus and just see how things would be split. It would be interesting to see how the choices would be a function of are you a quant person, are you a STEM person or not. Yes.
So I'm wondering why you go back to 50%. Like, why not go back to a spot where you have like a 70% shot?
Because we're assuming everybody has the same ability. So if you can make the shot 70% of the time, if you miss, you've already lost.
Yeah.
And if you win, then the person behind you has a 70% chance of winning now.
But then the chances that you both make that are like 50%.
But it doesn't matter. If you miss, you've lost.
Yeah. So why would you not want to give yourself like a better than 50% chance of making the shot?
Well, so let's say that the furthest shot that's been made is at the 70% mark. So that if you were to shoot there, you would make it 70% of the time.
Okay.
If you shoot from there, 30% of the time you lose already because you missed the shot. 70% of the time you still have a chance of winning, but then the next person has a 70% chance of making it, which is 49% of the time.
Yeah.
So 49% plus 30% gives you a 79% chance of losing. If you move back to the point where you have a 50% chance, so actually it may not be 50%. I'll put a question mark. If you move back to the 50% mark, if you make it, you have a 50% chance of winning. But if you don't make it, you've already lost. So your chance of winning would be only 25% of the time. Yes,
I think 50 sounds right because you're trying to maximize product of the probabilities of you making it and the person after you not making it.
right,
Just P times 1 minus P and let's maximize it.
right. So we can go into that in detail after finishing the pirates, and we'll circle back to that. But it's, where will you have the greatest chance? And the problem is, if you have a very high chance of making it, so does the person after you. And think of the extreme case where the basket is 100% chance of you making it. Then if you make the basket there and the next person shoots, they also have a 100% chance of making it, and you've already lost. So you have to go back a little bit so that they have a chance of missing. And then we can figure out exactly where. Oh, here. What I'll do is I'll just reorder the sheets. We'll do it now, and then I'll reorder the file later. So let's say you're here where P is greater than 50%. And here, I believe that this is the point where you would get it 50% of the time. And we're trying to figure out where should you shoot from. And so let's say you decide to shoot from some point. It will be a Celtic today. And I don't want to draw in the orange because it takes me too long to get to that. All right, so what is the probability you win if shoot, and this is P to date. If shoot at P. Well, you have to make it, and then the next one has to miss. So you would make it with probability P, and then they would miss with probability 1 minus P. So this is P minus P squared. So if you plot this, when P equals 0 or 1, you get 0. So the largest probability will be at 1/2. So your maximum chance of winning will be when P equals 1/2. And what will that probability equal? 25%. So if there's a high probability of getting the shot, because the person next to you has the same skill as you, you have a very low chance of winning. You only have a 25% chance of winning. What this is showing you is that if people are taking easy shots, you're in real trouble. My son and I actually played a modification of this when we were golfing. We went to the little putting range afterwards, and whoever went first, if you made your shot, the other person had to make the shot from one golf club, one putter length, base of the golf club further back. Well, of course, if the first person misses, then you can just put the ball, right next to the hole and just tap it in. And so with just two people, it all came down to where's the longest shot I have a reasonable confidence in being able to make it. All right, so going back to the pirates problems, we see that if we want to analyze this, we need more information. There's too much psychology coming in to come up with a good answer. So we have to make some assumptions about the pirates. So we're going to assume that these mathematical pirates. And their prime goal is to maximize expected value. So now, if we assume that they want to maximize their expected value, now what will happen when 3 proposes? So we had 5, 4, 3. 5 would do 0, 0, 0, 0, n. 4 would do 0, 0, 0, n, 0. What will 3 propose now?
0, 0, n minus 1, 0, 1.
0, 0, n minus 1, 0, 1. Because if pirate 5 votes against that, they get nothing. So what will pirate 2 propose? Clearly, they're going to give nothing to pirate 0. So to pirate 1, because pirate 1 is dead. So what will pirate 2 propose?
N minus 1, 0, 0, 1.
Yeah, n minus 1, 0, what's next?
0, 1.
They could do that. I think they would do something.
0, 1, 0.
I think they would do 0, 1, 0. If you do 0, 0, 1, Pirate 5 is actually indifferent.
But 4 needs to vote for 2 because if 2's proposal doesn't pass, then they get 0.
Exactly. And I think you end up getting alliances between the even and the odd numbered pirates. Right? What would Pirate 1 propose? 1 needs 2 votes.
N minus 2, 0, 1, 0, 1.
So n minus 2, 0, 1, 0, 1. And Pirate 1 knows that if this proposal is not accepted, then Pirates 3 and 5 get nothing, and 2 and 4 will split everything. So this is a great example of a wonderful concept. Start with a very simple state and work backwards. Because as soon as this proposal is rejected, we've now reduced it to an earlier problem we know how to do. So this is just a wonderful technique for attacking problems. Okay, any questions about either pirates or the basketball shootout? So the basketball shootout becomes a little bit more involved, but there is a beautiful, nice solution. Out of curiosity, how many people have seen this function before, pi of x? So this is the number of primes p less than or equal to x. It counts the number of primes by the prime number theorem. We get, pi of x is approximately x over log x. And I worked this into my talk at Brown. Why does this satisfy the requirement? I talked about pi rates. And so nobody noticed that I had done that until the end of the talk. We will have a technical malfunction, and I will share another story, but I do not want to share that with the video recording on. All right, so here's a integral problem. Integrate from minus infinity to infinity of sine of x over x dx. It turns out this is an extremely important integral. Why might this be a difficult integral to do? What are some of the concerns whenever you see something like this? So there's a lot of oscillation, which actually should help. Okay, what's infinite? So the interval is infinite. That's bad. What else is potentially bad?
What happens at 0?
What happens at 0? So there are two concerns about, is this integral well behaved? So a lot of times in math competitions, they give you integrals to do. And so the first thing you always want to check is this integral well defined? So the first thing is, the interval is infinite, so I have some concern. If I consider the integral from minus infinity to infinity, the absolute value of sine of x over x dx, this is infinite. So this means that this is actually going to be a difficult integral to do because you have to be careful. It is okay at 0. What is the limit as x goes to 0 of the sine of x over x? How do you prove that? We have 0 over 0. How do you prove that? You can't use L'Hopital. If you want to use L'Hopital, you need to know the derivative of sine is cosine. How do you calculate the derivative of sine? You have to look at the sine of 0 plus h minus the sine of 0 over h. That's this limit. So it is literally a circular argument because we're doing trig functions. If you try to use L'Hopital, you need to know that this limit equals 1 in order to use L'Hopital, because you need to know that the derivative of sine is cosine. So you have to prove from first principles that this limit is actually equal to 1. Okay, we will assume that you know that this is a 400 level class. You've seen this somewhere, or you can at least know, oh, you move your hands like that. So the first question is still on the board. Is this integral to converge? So let's consider another integral. So consider the integral from minus infinity to infinity of x over 1 plus x squared dx. What would you like to say this integral is?
You want to say it's 0.
You want to say it's 0. Why?
It's an odd function.
Yeah. It's odd function, symmetric region.
What's an odd function for you?
So that means f of x is negative f of negative x. So if you plot it, the value at positive 5 is canceled by the value at negative 5. Here's the problem. The definition of this is it's the limit as a and b go to infinity of the integral from minus a to b of x over 1 plus x squared dx. So this is supposed to be a 400 level senior seminar. This is a chance to tie and go back to some stuff that you haven't seen for a couple of years. When we do improper integrals, does that name sound vaguely familiar? You have to be careful about how do you go to infinity. And so if I take a equals b, what do I get? 0. If I take b equals 2a, this is the same as the integral from a to 2a of x over 1 plus x squared dx, which is approximately the integral from a to 2a of 1 over x dx. What function has derivative 1 over x? Log. I'm teaching too many middle schoolers and high schoolers calculus that I have to worry about base. Yes, once we're in college, log is always log base e. It's always the natural log. So I evaluate this at a and 2a, and this just becomes the natural log of 2. If I had taken b to be 3a, I would get the natural log of 3. I can get this integral to equal anything I want, depending on how I go to infinity. So this integral does not exist. This is related to the Cauchy distribution in probability, where the density is 1 over pi, 1 over 1 plus x squared, if you've ever taken a good probability of stats class. So this is a distribution that does not have a mean. It does have a median. What would be the median for this? Where half the probability is before this and half the probability is after. It would just be 0. Okay. So let's go back to the integral from minus infinity to infinity. Previous integral does not exist. If you take the absolute value of the integrand, it's plus infinity. And if I don't take the absolute value, it depends how I go to infinity. So let's look at this integral. And again, I'm trying to just do topics that you hopefully have seen a little bit of in earlier classes, but maybe some points have been missed. And these are just, some things you should see before going on to infinity. We have to worry about how this goes to infinity. What can you tell me about sine of x? So this is going to be oscillating positive, negative, right? And so if I plot sine of x, it's going to look something like this. Oops. Right? Now, if I plot sine of x over x, what's that going to look like? Well, sine of x over x is going to start off at 1, and then it's going to be getting smaller. And we know it's going to somehow get down to 0 over here. Then it's going to become negative, but then get back up to 0. And it's going to somehow be getting tighter like this. It's going to be alternating between positive and negative. And so what we can do, sine of x over x is an even function. So if I can just figure out what's going on from 0 to infinity, I can go backwards as well. I can break this up as to an integral from, let's say, pi n to pi n plus 1, and then a sum n goes from minus infinity to infinity of sine of x over x dx. In each of these regions, it's either going to be always positive or always negative, right? And so what can you tell me about the values? So I'll write this as sum n goes from minus infinity to infinity of in, where in is the contribution in the region n. So what can you tell me about, say, I5 versus I6 versus I7 versus I8?
They have alternating signs and also they decrease with n.
Alternate sign and decrease with n if n is greater than 0, similar if n is less than 0. So they alternate signs because in the first one, everything is positive, the negative, and positive, the negative. So we have alternating signs. And then we're dividing by x. So notice that the blue curves are the same. They're just shifted over by pi. But in the first one, I'm dividing by smaller x. And the second one, I'm dividing by larger x. So the contribution is going to be smaller in each one. So each one, I'm going to have an alternating series of decreasing terms. So what do you know about an alternating sum of decreasing terms? If it's initially positive, it will be positive, but does it converge or could it diverge? It converges. So this is one of our convergence tests. So the way you can look at it is, imagine we start off, here's the first one, here's A0. And then we come down, here's A1. Then we go up A2. Then we go down A3 and so on. So it's alternating, so the contributions are going in opposite direction, right? When we take A0 and we go down by A1, we can't go down lower than when we started. Then we add A2, we have to go up a little bit, but we can't go all the way back up to A0. So the new high is lower than the old high. Then when we go down by A3, we go down from where we were, but we can't go all the way down to where we were before. So you're going to have some kind of envelope. So this is a quick rough sketch that this sum actually converges. So even though it's alternating, it doesn't matter how you go off to infinity. So the limit as, let's say r goes to infinity. Oh no, we'll do a and b go to infinity. The integral from minus a to b of sine of x over x dx exists. So this proves that the limit exists. It doesn't prove what the limit is. Anybody have any ideas how we would try to calculate this? We did mention the technique earlier in one day. It's a one-day blitzkrieg of a subject. Contour integrals. I'm not going to go through this in details, that we do have ways to solve this. So contour integrals. So what we're going to do is here's minus r, here's minus epsilon, here's epsilon, and here's r, not drawn to scale. Okay? And what I'm going to do is I'm going to look at the integral of e to the iz over z dz. What is e to the iz? That's cosine z plus I sine z. Well, let's do x. So if I happen to take a real value, e to the ix is cosine x plus I sine x. Look at this function when the variable is real. That's good. It's looking a lot like sine of x over x. The problem is I also have cosine of x over x. Well, what kind of function is cosine x over x? Odd. And so if I look at the integral, if I take the limit as r goes to infinity and epsilon goes to 0 of the integral from minus r to minus epsilon plus the integral from epsilon to r of e to the I x over x dx, this is just going to go to the integral from minus infinity to infinity of sine of x over x dx. Because cosine x over x is odd, so it's all going to cancel out. So now I just have to find a way to complete my contour. And what I'll do is, I'll go around like this, and then I'll come back, whoops, like this. And there's one pole, and the pole is right here. And so the pole is outside, so you have to figure out what goes on along one of the poles. Normally in complex analysis, when you go along the top contour, you want to say that things are just small. The problem is, if I look at e to the iz over z, well, if I bound the exponential, the denominator gives me a 1 over absolute value of r, but what's the length of the upper semicircle? Pi r. So I need to somehow exploit some cancellation in the exponential. And I just want to give you a sketch of how you do problems like this. I understand most of you have not done complex, but some of you have. And every now and then I just want to throw in some of this material. What we can do is the following. So here is 0. Here's my contour. And what I'm going to do, again, not drawn to scale, is I'm going to have some angle theta of r. And now let's look at e to the iz over z. This is e to the ix plus iy over x plus iy. And I want to just see how large is it. Well, this is e to the ix, e to the minus y over the absolute value of r, because I'm on the boundary. E to the ix is absolute value 1. So this is just equal to e to the minus y over r. So as long as I'm a little bit up, I'm going to have some decay from the exponential. So if I can just ensure that I start up a certain height, I'll be okay. And as long as this length over here is sufficiently small, then when I divide by the r, I'm okay. So for example, imagine this was of size, say r to the delta, for some delta less than 1. Then if I wanted to figure out what is the contribution of integrating this over those two things, well, it's at most the length of the arc times the largest value. So if we call these like the little blue fringes on blue, it's going to be less than or equal to twice, then it'll be pi r to the delta times 1 over r, and that's going to go to 0. And now if I look on the other one, I want to basically get a sense of, if that's of length r to the delta, theta has to be at least so large, how high must I be? Can you give me some idea of what my height must be? And so you want to just show that there's enough so we have some decay here. Well, so we just have to figure out exactly what's going on. So, if we draw it over here, we've got, here's our blue arc. We're coming, top line, coming up like this. Here's my right angle. Here is theta r, which we're going to assume is, well, this blue length here, we said was r to the delta. The whole thing has length 2 pi r. So this angle is going to be r to the delta over 2 pi r. It's going to be a very small angle. The radius is r. This is going down here going to be cosine theta r times r. And over here, this is going to be r times the sine of theta r. So the height, which is y, is at least r sine theta r, which is r sine r to the delta over 2 pi r. But when the angle is really small, the sine of x is approximately x. So this is approximately, r times r to the delta over 2 pi r, which is r to the delta over 2 pi. And the next term is going to be minus the cube of this over 3 factorial. So it makes it even smaller. So this is going to be fine. So if you put in like a 1/2, you're safe. So this proves that y is going to be at least r to the delta over constant if you do this. And so now when you come back over here, you're going to have enough decay. So just showing us an interesting complex analysis contour integral. There are ways to do this. We can at least prove the integral exists. And this is a chance to just review some integration. All right, good place to stop. I will send details about the exam